Hello.
Hello, sir.
Yeah, so I do see that there is a huge number of participation in the class today. So I don't know. Did you have some other classes before this or something?
Yes, sir. We had a parametric class which
Hmm.
actually extended a little bit, like
Okay.
for further. I don't know. It's because of this or that, but it extended, sir. That time is extended.
Good. So should I wait for some more time?
Sir, I can drop a message on the group, sir. If
Yeah,
you can
sure.
wait for 2 to 3 minutes and
Sure,
then.
sure. I can wait for 2 minutes. This. Okay, so let us start today. So yeah, so before I start, any questions on whatever thing that was done in the last class?
Yes, sir. Can you just clarify the concept of reduction? I understood.
Yes.
Somehow notationally, I was got a little bit confused. Like, if there are two problems,
Hmm.
L1 and L2,
Hmm.
and if knowledge of L1, if I know how to solve L1,
Hmm.
that implies I can solve L2.
Yes.
Then that notation will read L1 less than equal to L2. So I'm confused in the notation part.
Okay. So let me. Yeah. So the way in which you can think of it is that, see, you have two problems, L1 and L2. Okay.
Yes, sir.
So if you know how to solve L1, say in polytime, then you can solve L2 in polytime. Now, in this case, which is harder? Is it L1 the harder problem or L2 the harder problem?
So L1 is the harder problem.
L
No. L2 should be the harder problem. I don't.
Sir?
So think of it this way. Yeah, go ahead. Yeah.
Oh, no. No, sir, after this.
Okay. Yeah. So think of it. So your friend is there. Okay. Your friend. Okay. Knows to solve something. Okay. He can solve something. You have a problem. Okay. If you can reduce it to the problem that your friend can solve, okay, then you could be able to solve your problem.
Yes, sir.
Now, in that case, who is which is harder? Who is the most smarter, you or your friend?
So the person who's reducing. I mean, I am ready.
So you reduce. So you have a problem that you have to solve. Okay.
Yes, sir.
Okay. So you and your friend has another problem that he knows how to solve. Right. So you have taken your problem, changed it to the problem that your friend is able to solve.
Yes, sir.
And then you use your friend to solve it.
So that is the critical step where I transform it to something where I reduce it.
That is I'm not saying that the reduction part, it's of course critical, but which is harder? Which problem is harder? Your problem or your friend's problem?
My problem, because I have to first reduce it, change it, and then go to my friend who already has a solution.
But maybe your friend has a solution for a much more harder problem.
Okay.
So think of it this way. It's like the mathematical concept of, if you know how to solve Riemann hypothesis, you can solve a simple conjecture. Right. So someone, your friend is saying that I know how to solve Riemann hypothesis. So how will you do it? You have a problem which is a simple problem in number theory. You convert it and say that, okay, now this is an instance of the Riemann hypothesis. So by Riemann hypothesis, this follows. Right.
Okay.
So we can think of L1 as a corollary of L2, right?
L1 as a corollary of L2. Exactly. So no, not L1 as a corollary. Which is a corollary? See here, which is same thing. So how will you solve this thing? In this case, it is not the L1 which is corollary of L2.
Right. L2 is the corollary.
If the L2 is the corollary, so because you have been given L2, you change it to some other problem, right? You change it to L1, and then you use the algorithm to solve L1, right? So in some sense,
Yes, sir.
L2 is a, as somebody says, I will use the same word, is a corollary of L1. Okay, it's like you have a problem, you have used something, and they said, okay, by this theorem, this follows. Now, what is that theorem? Oh, that theorem might be a much more harder theorem. That I don't know. Okay. So in some sense, what is happening is that L2 therefore is easier than L1. Okay. So this is how we will note it. So for example, this is a statement. For all language in NP, L reduces to that. Let me just quickly see this whole notation once again, so I don't make a mess of this thing. Yeah. So this is the notation, yes. Okay, so this is says that L reduces to SAT. Is this clear?
Yes, sir.
Okay. I mean, I also am.
That
Yeah.
hello.
Yeah.
Then
Go
that
ahead.
isn't that that means that SAT less than equal to L, because L reduces to SAT is like if I can solve L, I can solve SAT, right?
No. Exactly the opposite. L reduces to SAT.
Okay, L reduces. Okay, SAT reduces. Okay. L reduces to SAT. Okay.
I mean, it's like it's the reduction meaning. I mean, that's same thing, right? So you have a problem, you have modified it and converted into an instance of the, I mean, where you are going to apply the Riemann hypothesis. So you have converted this problem to an instance of Riemann hypothesis.
Yes, sir. So basically, the thing on the greater than side is like a black box. So I mean, everything else is reducible. If that black box is solvable, then everything else on the other side is solvable, right? Something like that.
Right, exactly.
Okay.
Now, if the one in the right hand side is solvable,
actually, sir, that is why I asked, because when words are converted to these notations, sometimes we have a tendency to misinterpret. So I think I get it. I understand it. So
yeah, I mean, I must say that it's not necessarily the most. I mean, although it's a pretty consistent notation and pretty logical notation also, but I also have this problem of suddenly when I have to explain someone, I forget which reduces to what. But in my mind, I know that what is the harder one and which is the easier one.
Sir, so in general, the right hand side, the thing is the harder one, right?
In general, the right hand side is the harder one.
Okay, sir. Thank you.
So actually, we will see more of this thing today. Actually, we will see some examples of what is this about proving. How do you prove something NP complete and so on. But yeah.
Sir,
Any other? Yeah.
sir, another question was, sir, Anurag and I were discussing a certain thing where if P is equal to NP, we know that NP complete will be a subset of P. And we wanted to show that they will actually be equal then.
Correct, exactly.
So we were approaching it in this way where what if we can prove that P itself is equivalent? Any two P problems are equivalent.
They are in some sense. Why?
So all the
So if I take
reducible to each other.
Right. Now what does that mean? Okay. So this is actually, so LNA is in P, then L1 reduces to P. Now this basically means that, okay, what does this statement mean? Okay, so you should not think of, so this is not less than, okay, it's less than with a P in it. What does this statement mean?
So we can find a polytime reduction.
So okay, let's just look at it in a very this very definition, I mean pure definition thing. Okay,
Okay.
So if there exists an algorithm, okay, so maybe you can call this one a reduction if you want to call it R, okay, that is taking a string to another string such that for all x in L1, okay, R of x is in L2 if and only if x is in L1, and R is polynomial. Okay.
Yes.
Okay. Now let's see. Why is such a thing obvious? Why does there exist an R obviously for this setting when L1 and L2 are both polynomial, are both in P? See, what is it means that L1 is in P? What does it mean?
So we have to convert x to Rx given some polynomial time.
Hold
right?
on. Forget Rx to Rx. What does
So for
L1 means P means?
For an instance, we can use an algorithm of polynomial time to find an solution. I mean
Right.
answer.
So there is an algorithm A, right? So this is to 0 and 1 such that for all x, A of x is 1 if and only if
X belongs to
L1, right?
Yes, L1,
And A is
yes.
polytope.
Yes, sir. Yes, polytope.
Okay, maybe I should use a different color here. Maybe I should just draw up. So the top one is a reduction, second one is a question of what does it mean to be a polytope. So what does it mean? So I already have an algorithm, right? So what is the natural algorithm that I can do? How will I get an R from A? So you've given me an X in L1. My algorithm will do the following. It would, first of all, it fix number, okay, fix a number y0 and y1 such that, okay, y0 is not in L2 and y1 is in L2. Sorry. Fix it. I don't care what is it. Just two numbers, two strings. Okay. And how? Yeah.
So we need some y1 and some y2, which is corresponding giving us a yes or and a no for L2, right?
Yes, for L2. That's just two things. That's all. I mean, it's not a variable length and all those things. Okay.
So, but then how do we know we can find y1 and y2 in polynomial time?
We know L2.
Right.
We know L2, right? So we know that there exists such a y1 and such a y2. That's all.
So we know there exists, but do we need to find them out, or we just?
No, we
need
don't have to find them out.
Okay.
We don't have to find them out, right? You see, again, none of them are the algorithms. Right? It is in P if there exist. It reduces if there exist. Now, that's a different issue of you kind of coming up with an reduction. That's a different thing.
Okay. Right.
But the algorithm says, the definition just says that if there exist.
Okay.
I mean, you
And
have
now
not
we
been
can
able.
just.
Yeah.
Right. Sorry.
So and see these two, well, you can say that what is the guarantee that they are polytope? Polytope in what? They are just two numbers.
Right.
It is not a variable length, right? It's a fixed length.
Yes,
A
sir.
fixed length is always polynomial. I mean, because it's a constant. It's an order notation that we are using, right?
Right.
I mean, maybe this is of size 1 million and this is of size 1 billion. But 1 million and 1 billion are constant. They don't change.
Right.
Okay, period. I mean, they just get stuck.
Yes, sir. Yes.
Okay. So what would my algorithm R be then?
So we just use A to solve L1, and
Yes.
if it is coming out to be yes, we can map it to y1.
Exactly.
If it comes out to be no, then we can map it to
Exactly.
y0.
That's it.
Okay. Right. So we don't actually need to determine any reduction. We know that there exists such a reduction, so
Yes.
it has
So
to be.
it's not a reduction just because it's a polytime reduction. That's why this whole trick is working.
Right. Okay. Yes.
Reduction is itself like kind of algorithm.
Yes, reduction is an algorithm. Yeah.
So we can always use a, I mean, we can always reduce a P problem into any other problem.
Yes, with any other P problem.
With any other problem, like it
Any
doesn't
other
even have to be-
any other problem. That's true.
Correct. Okay.
Okay. A P problem can be reduced to any other problem.
So it's like the minimum problem in this
Correct.
whole set of problems,
Right.
minimum
right.
complexity.
Yeah.
Right. Okay.
Okay. So this Cookley theorem that I told you, the interesting part is the problems which are not necessarily in P. Prove that one reduces to SAT, that is the more trickier part. Things that are in P, they're obviously reduces to SAT. Okay.
Sir, just for clarification, this Cookley theorem says that there exists a set, right?
No, so I kind of gave you the SAT instance yesterday. Let me give
Yes, sir.
you
Yes,
the
I just forgot actually.
Yes, I will let me give you the SAT instance once again. Okay. So, okay, so let me give you a slightly lesser version of SAT. It's called the 3 SAT. Okay. Okay, and this is kind of this is equivalent. This is also NP complete. Okay. Now, so now what is a 3 SAT? So you have variables. Okay. So these are called propositional variables. So they are called the propositional variables. So say it has x1 to xn. So they will take values from either true or false. Okay, and you have clauses. Okay, so let's call this one. You have a formula. What is the formula? A formula is you have a say x1 or x3 or x5 bar. Bar meaning the opposite. Okay, meaning. So are you guys familiar with this this thing?
Yes, sir.
This
Yes,
notation?
yes, sir. Yes, sir. Yes,
Yeah.
sir.
Okay. So and x2 bar or x3 or x5 and something. Okay, it goes on like that. So this is called a 3 SAT. So why 3? Because each of them, so these are what are called clauses. So okay, this is a clause 1. Okay, these are called clauses. So clauses are just odd of 3 variables or 3 literals. So each of them is called a literal. So I can either give you x5 or x5 bar, right? So these are called literals. And a clause, these are called clauses. C1, clause C1, clause C2, and clause C3, and it goes on. And each clause has exactly 3 variables. Okay. Now, so this is a formula. Okay. So the 3 SAT problem is, what is it? So 3 SAT problem has the input is a formula. And the output is 1 if and only if there exists an assignment such that the formula is satisfied. Formula is satisfied or formula evaluates to true. Is this fine? Hello?
Yes, sir. Yes, sir. This is fine.
Yes, sir.
Yeah. So who was the person who asked the question? I forgot. Are you there?
Sir, yes, sir. I'm here.
Yeah. So
Yeah,
is it,
it's fine, sir.
it's fine, right? So I
Yes.
am not going to give you a proof that this is NP complete, okay? And I told you guys that I want you guys, whoever is interested, please look up in the internet or the books to prove. Okay, so this is a theorem, and I am assuming it. Okay, I am going to assume. This says that for all L in NP, L reduces to SAT. Okay, I mean, I will be calling this one SAT for all purposes. Okay, 3 SAT. Or in other words, SAT, or what you call 3 SAT, is NP complete. Oh, by the way, I have told you this is NP complete. Now there is also a concept of NP hard. How many have you guys heard of it?
Yes, sir. We've heard some of us.
Yes.
Definitely.
So what is the difference between NP complete and NP hard? So there's a very fine difference between these two. Let's look at this problem, this SAT problem. What does SAT problem? What all things can you say about the SAT problem? Can you solve this SAT problem in poly time? Or can you solve it in exponential time?
Sir, exponential time we can do.
Okay,
because
how?
it's NP.
How? Can you just quickly tell me?
Sir, it's an NP problem, which is an exponential problem.
It's an NP problem, right? Why is it an NP problem?
So because it is okay, given a yes, so a witness could be an assignment of exercise.
Witness the assignment of exercise. So somebody gives me an assignment of exercise, and all I have to check whether that assignment actually makes this formula evaluate true or not.
Yes, sir.
If it evaluates to true, then we are done. Now, checking whether a particular assignment evaluates to true or not is actually a polytime algorithm. I am not explaining you exactly how, but you go ahead and think about it.
Yes, sir. That is I think
that is clear, right?
That is clear, sir. Because of yes, sir. That is clear.
Once you are given the assignment, so this is an N. It's a problem in NP. Okay, so NP hard. So these are. Let me just define you. Will I give you the formal definition? Okay, let me give you the formal definition. Okay, so these are all the languages L such that all languages, okay, such that for all languages L tilde in NP, L tilde reduces to L. So these are all the problems that are harder than all the problems in NP. Okay, and NP complete is nothing but NP hard intersection NP. So it's not something. So there are problems which are much harder than NP. So they are way out there. Something like whether chess has a winning, whether there's a winning strategy of the first player in chess or not. Okay. So that is also NP hard, but that is not in NP. Okay. So so since we kind of these two statements, or NP hard and NP complete, are kind of used interchangeably, because the difference is actually, I mean, it's like almost clear from the context what we are meaning. Okay, so but this is basically it. So if you have to prove some problem with NP complete, technically you have to prove it is NP hard, and then you have to prove it is in NP. Yeah.
Okay, sir.
That's right. Okay. So I am going. Yeah. Go ahead.
So So if the best we can do is some exponential to the power exponential, then it would be NPR.
Any problem that is exponential to the power exponential, they're the NP hard. Yeah.
Okay.
Any problem which has a lower bound of exponential to the power exponential is NP hard. Yes. Any problem which is even harder than, or for which there is no lower bound of slightly more than exponential itself, then it is NP hard. Okay. This one. Yes, sorry. Yeah. So any questions? Any other? So I am not going to prove this statement, okay? I am not proving it, I'm telling you, but this is a theorem. I don't know how to more to emphasize it. This is a theorem, okay? So this theorem is it's not a Murphy's law kind of a law, okay? This is actually a theorem. Okay. Now, how do you prove it? Okay, you have to prove it via the concept of Turing machines and all those things, and therefore I am not going into it. Whoever is interested can read it. Okay, but our job will be to, after assuming this theorem, to prove something, some other class of problems to be NP complete. For example, can we prove that ILP? Oh, sorry. Can we prove that? May I use a different color? Yes. Theorem, say. Integer linear programming is NP complete. Let's see, can you prove it? Hello, do you guys remember integer linear program?
Yes, sir.
Yes, sir. We do.
Yes, sir.
So it's a linear program where you are given the extra condition that the variables are integers, right? The variables has to be integers. You cannot put variables to be anything but integers. Now, how will you go about proving it?
Sir, maybe SAT we can use. Somehow we can relate ILP to SAT and then like try.
Right. See, one thing is notice that since ILP, first of all, first statement, ILP is in NP. I am not proving it. You guys have already discussed this earlier. Right. No, okay, what is ILP? Maybe I should kind of write it properly. So what is ILP? So ILP basics, sorry. So you have been given, and so this here, you have been, what is this problem? Okay, so you have been input is a linear programming instance and a value k, and the problem is that output 1 if there exists, and so is there exists an ILP solution that is less than or equal to k. So yeah, so less than or equal to k, and zero otherwise. Right. So it's a, I have to convert it to a decision problem, right? So this is the decision problem that I'm talking about. Now, why? So my claim is that ILP is in NP. Why is it so? Can somebody say why is it ILP in NP?
Sir, we just need to check for the witness of an assignment of integer values.
So what is the so the witness is the assignment, right?
Yes, sir.
The witness is the assignment, and we have to check whether they satisfy all the conditions.
Yes, sir. And then we calculate the optimization function if it is lesser than k.
It's k or not. Very good. Okay. So number one, ILP is in NP. So which means that ILP is less than or equal to SAT. So SAT is the hardest, we know that. But to prove this statement, I want to prove that SAT is less than or equal to ILP. This is what we want to show. Okay, to show. Now maybe let me give you guys just 2 minutes to think about it. How would you try to solve this statement? So there are yeah. So please individually try it. What does it mean? How would you prove ILP is SAT reduces to ILP?
Sir.
Hmm?
Oh, okay. Anurag, you can go ahead.
So when you're saying SAT, you're using this 3 SAT thing.
Yeah,
only,
I'm
or-
using 3 SAT. I'm using 3 SAT. So
Sir,
maybe you want me to produce this thing, 3 SAT thing? Okay, this is 3 SAT.
So SAT in general is NP hard or NP? Is it NP complete?
SAT is also NP complete. I mean, SAT is basically same. You just add a extra more,
Oh, okay.
a few more simplifications. That's all.
Sir, so the problem is all the decision variable that we have in the linear programming problem. Somehow, if we can associate indicator variables with them, such that whenever any particular instance has a value less than equal to k, then this circuit will give on like output 1 something. I don't know. We can try, but I don't know how to
think. You are in the right direction, but think. Okay.
Okay, sir. Wait, I'll try to make it concrete.
Sir, in the 3 SAT, is there any upper bound on the number of clauses?
No. That's another parameter, M. Okay, so the input is basically, you can think of 3M, if that matters. 3M plus N is the input.
Okay, but then we can always bound the number of unique clauses we can make.
Yeah, but that's also a lot. That can be a lot. That is that is bounded. There's N choose 2.
Right. Okay.
Or actually, yeah, 2 N choose 2. Yeah.
Sir, can you scroll down, please? To the decision transformation of ILP to a decision problem. So we are saying that the ILP instance is so ILP instance is there and a value k, output 1. So there exists an ILP solution less than equal to k. By this, sir, what do you mean exactly, sir? The solution will be, so we have a region usually, right? In LP you get a
So if I want to formalize it.
Yes, sir. So that is why, to make it concrete, we need a formalization maybe.
Yeah. Okay. So before I formalize this whole thing, I have to kind of. So when I am talking about x, so this is a vector of x1 to xn. Okay, it's a set of variables.
Yes, sir.
Okay. I have a c. It is also a vector. Okay. So this is r to the power, rn. I mean element of rn. Okay, so it's a vector you can think of. Okay, c1 to cn. And I have a vector similarly, vector b, which is also an rn. And I have a matrix, which is r to the power n cross m. N cross m? N cross m. Yeah, m cross n. Okay, so it's a matrix. The idea is that you can think of them as the columns that are labeled as for m of them, and then these are the clauses or conditions c1 to cm. But not clauses. I mean, don't confuse with the SAT clause. These are the conditions. Okay. Now, what is an ILP? So you want to do is that you want to say maximize or say minimize, doesn't, we can do it with minimize. Minimize C transpose dot X. What is C transpose dot X? It is summation of
scalar.
Xi
Yes, yes, it's an inner product. Yes.
such that, okay, A dot X is less than or equal to B. What do I mean by that? So A dot X is the,
Vector.
this has to be M,
Component wise less than B, right?
component wise less than B.
Yes.
Okay, and I want X to be, usually it is written as like this, X is greater than 0. Okay, and X is in the reals or Z or natural numbers. Yeah. So what means this is actually n to the power n. Okay, so this is an ILP instance. Okay. So in the case of the decision problem, you have also been given a K. And the question is that, is there an instance that makes this one or this CT dot X go less than K while maintaining all of them?
Okay, sir. Got it.
Okay, so this is the formal definition of an ILP or an LP, whatever you want to call it. So it's only at here that the ILP and LP differs. If it is R to the power n, then it is LP. If it is n to the power n, then it is ILP.
So could you scroll up to the 3-sat problem?
Just think, when does such a formula become true?
Sir, when all all clauses are true, only then it will become true, right?
Right?
So
Because it's the and here.
and operators are there. Correct, correct. So at least one of the statements in each class must be true.
Sorry?
At least one of the statement under each class must be true.
At least one of the literals.
Yes, literal. Okay. So under one of the, at least one literal under each clause must be true.
Right.
But that doesn't complete the. We need odd number of them to be. So either 1 or 3, right? If 2 of them are true, then the other one is false. Then also it won't work.
No. Why? No, it's not an XOR.
Oh, okay, right.
It's an OR. It's not an XOR. It's not an exclusive OR.
Yes.
It's not a parity that we are doing.
Right. So if we're looking at the 1, 1, 1 vector,
Which vector?
the 1, 1, 1 vector, and if we take a dot product with any one of the clauses, if it gives us 1, that means at least one of them was 1.
Okay. At least one of them was 1.
Oh no, sorry. Just.
Okay. Let me ask you here. What happens if there is no X that satisfies this?
So it should return 0.
It should always return 0, right?
Yes, sir.
It doesn't matter what the K is. right? Yeah. Now think of it.
So could you repeat?
So in this ILP, if there is no X that satisfies these conditions,
Yes, sir.
there is no X. So this is not a solvable set of inequalities.
Yes, sir. So I guess I guess we can like break down this condition into binary true false things, and we can encode that thing. But the main problem that I'm facing is like how would I include the minimizing thing into
Don't
the
include. That's what I was thinking. Don't include. Don't include.
so if we don't include, then there might be multiple answers that gives one right in the
Okay.
when we
So
have
let us look at the first hint. Okay. What happens if I can you take this such a SAT instance, okay, and convert it into a set of equations such that if it is satisfiable, then this set of equations is satisfiable, or otherwise not. So what I will take is that I will take an instance in SAT. Okay, so maybe it's not there. This is called a CNF. Oh, by the way, when I just told SAT, I might also be using this thing. It's called the CNF also. The conjunctive normal forms. Okay. So don't get surprised if I suddenly use this word CNF. Okay. So sometimes it's called CSAT, sometimes it's called CNF. Okay. So in fact, these are called the CNF formulas. So whatever we are dealing with, it's called CNF formula. So CNF formula 5. Okay. So my job is to map CNF to a set of inequalities such that the formula is satisfiable if and only if the inequalities are satisfiable. Now, part is that if it is so, okay. So what happens here? In that case, I can take K to be any number that I want, maybe a massive number. Okay. All right. I have this C in my hand. So sometimes what we define here is this one. Okay. Minimize 1. 1 meaning it is nothing. I am asking you to minimize the constant, minimize 1, not such that these things are satisfied. What does it mean? When can you? Sorry,
Then we've forgotten about the optimization. We're only
I have
looking at
forgotten the
whether
optimization. I'm just looking at whether the inequalities are satisfied or not.
right.
Okay. If the inequality is satisfied, output 1. If the inequality is not satisfied, you are outputting nothing. Okay. So you can have this K to be equal to K equal to 1. Say. So question is that can you do this? So I have a CNF formula and I want to write a set of inequalities in such a way that if psi is satisfiable, if and only the inequalities are satisfiable.
I think this can be done, sir.
yes.
Sir, I think there is some.
Okay, so I hold on. It surely can be done. Okay, you guys just try to solve it yourself. Okay, just 1 second. Let others who have not been keeping up maybe. Let me just try to write down the inequalities formally in your notebook. Just take 2-3 minutes. I want you guys to do it. Okay. By the way, this is what I'm doing is very important because, I mean, not only is it important as a problem in or as an important subject in the algorithms, but also this is exactly what I mean. This is the big chunk of the course end sem that will be there. I will be asking you to solve various problems to be proving various problems to be NP complete. Okay, so please just try to solve it. So let me just go to the restroom and come. So I will give me 2 minutes and while you guys try it. Do you want me to flash the SAT instance? Okay. Is this better?
Yes, sir.
Hello. Did you guys manage to?
Yes, sir. Yes, sir. I think I got it.
Yes, sir.
Sir, under each class, what we can do is, so we have basically AX
So
less
tell
than
me what
equal-
are the variables, first of all?
So the variables are the BI minus AX size. If that is greater than 0, then 1, otherwise 0. Like that
BI
is
minus AXI.
yes, sir. The
The
AX less
summation AJI xi smaller than BI. That would be, I guess.
No. Forget. I'm asking the variables, not the inequalities.
Sir, x1 through xn.
X1 to xn is the variables. Okay. Okay. So let's see what happens in that case. Okay. Let me try to draw some holes in your argument. So someone here is saying that let the variables be x1 to xn. Okay, fine. This is the variables. Now, what are the inequalities? Okay, so let me try to give you a clause. So clause, the first formula, just tell me this one. Okay, the formula is x1 or x2 or x3. What will you? So if this is the formula, what will be the inequality? Just this. That's it. Only one thing. What will be the
So
inequality?
all xi's should be between 0 and 1. And 1 minus x1 plus 1 minus x2 plus 1 minus x3 should be lesser than equal to 0.
Equal to 0. Okay, so what is the argument?
So that if we want every single clause to be 1, what we need is at least one of these literals to be 1, which means we want all of the negatives of these literals to be 0.
No, at least one. So that means literals at least one has to be 0.
Oh, okay, right. Sorry.
Sir.
Yeah.
Sir, I am proposing the following variables. So that is, one is indicator. So we have m inequality under the inequality ax less than or equal to b. We have m equations, right?
Yeah, you can have m. Yeah, whatever.
So
but
corresponding to those.
By this m and that m has no correspondence. Okay, you can choose your m and n. M and n can be anything.
Yes, sir.
Okay,
so corresponding to those m, I am considering m indicator variables.
Corresponding to which m?
So the m equation. So a11 x1 plus a12.
Hold on. You have been not okay. That's the first part. You don't want to start from a ILP instance. That is the first thing that you have to do. What do you start from? Consider this one. What is it that we want to prove? We want to prove this part. SAT is less than ILP. So it is not that we start from an ILP solution, write a SAT formula, and then say that done. That ILP has a solution if and only if SAT has a solution. It is the opposite. You start from a SAT instance, then put it to ILP and then solve it.
Okay, sir.
Okay, this is the first very, very important thing. This is something that we make mistakes continuously. Okay, this is very, very important. We want to prove. Okay, so say to prove ILP is NP complete, we have to show SAT reduces to ILP. So what does it mean? That means you start from a SAT instance. Okay, free. And then you convert it into a ILP instance. If you do the opposite, okay, so you might think that, oh, this is an if and only if thing. No, it is not an if and only if thing. As I told you last time, you take an instance, convert it to an inequality. And you're saying that this is satisfiable if and only if this inequality is satisfiable. What is this inequality? It's not any inequality, but the inequalities that are mapped by phi. Yeah, that is the range of the actual range. Okay, so you start from a SAT instance and then you try to write a ILP instance. Is this clear?
Yes, sir. So, okay, I get it. So, sir, if we consider a clause inside a SAT,
Yes.
let's say Z1, so let's say it's like this, Z1 or Z2 or Z3.
Mm.
So more precisely, it should be Z1 or Z2 bar or Z3 bar. So
Z1 or Z2 or Z3, or you want
Z2
to
bar,
bar?
Z2 bar and Z3 bar.
Oh, okay,
So
say.
Z1 I want to map to, so I have three sets. One is that Ax less than equal to B, one is X greater than equal to 0, and one is X natural number. So under each bracket, I want to have one true and the remaining true as false. Like, how to say this? Like, if let us say,
Hold on, hold on. This Ax less than equal to B is not a single thing, you understand, right?
yes,
This
I
is
know.
a combination of a number of inequalities.
Yes, sir. I'm just talking about, let's say, one inequality. So what
Right.
I'm considering Ax less than equal to B. I'm just considering at individual levels, like for what my clause structure should be. So my clause structure should be that it should reflect like one variable Z1, which I want to map if it is true there. The Z2 bar and Z3 bar is actually we want true here, but inside the bracket we take the negation of it, so that whenever this bracket is on implies that Z1 is on. So
I guess we can just write Z1 VZ1 VZ1, then intersection with the Z2 Z2 Z2, intersection with Z3 Z3 Z3, then that thing might work.
I didn't follow you at all. What is the intersection that you're talking about?
I mean Z1 that union Z1 union Z. So we are supposed to.
Or yeah, so this is I'm saying if this is the clause, this is the formula. Okay, how will you take this formula? How would you write ILP for this formula? What the inequalities for this formula?
So I know inequality which has a greater than equal to sign, which is something
That's
like,
fine, perfect. Greater than or less than or same.
so
You
but
are mathematics students.
okay, so something like Z1 plus 1 minus Z2 plus 1 minus Z3 should be greater than equal to 1.
Z1 plus 1.
1 minus Z2.
So 1 minus Z2
plus 1 minus Z3 should be greater than equal to 1.
See, this is good enough. Okay, why? First of all, because this is same as now you say, oh, you have written Ax less than B. Isn't this a form of Ax less than B?
Yes, sir. But then aren't there restriction on the A matrix to be something like a positive or negative or something like that?
There is no restriction on A.
Okay. Right.
There is no restriction on A. There is no restriction on B.
Okay.
So this is nothing but you multiply it in -1 both sides, you get a negation less than, right?
Right.
Okay. See, this is good. So you are saying, okay, so this I would like to write it here. Why? So if I have a thing that I want to, if you put if Z2 is 0, then you have
so either we want Z1 to be 1 or Z2 to be 0 or Z3 to be 0. So if either one of those things happens, then in this sum either Z1 will become 1 and the rest will only increase it beyond 1, or if Z2 was 0, then 1 minus Z2 will become and the rest will only increase it beyond 1, and so on. So every single term here is just representing whether we are able to achieve either one of these cases which gives us a true value for the whole clause, then that inequality will have to be more than 1. And this whatever this sum comes out to be is how many of the number of literals actually achieve the value of 1, which we only just want one of, we only want at least one of them to achieve. So that has to be greater than equal to 1.
Excellent. So if I have to write it properly, okay, so here it is. Okay, so I would like to say, okay, so let phi be a CNF formula. So phi equals to C1 and C2 till Cm. But each Ci is a clause of the form, what is it? Xi1 and also not and or Xi2 or Xi3. Right? Good.
Yes, sir.
Now let's the variables. So consider the following instance of ILP. What is it? First of all, I have to define the variables. Variables. So here also there is the formula, right? There are the variables x1 to xn. The variables are still x1 to xn. Constraints. Okay, what are the constraints?
Sir, all xi need to be 0
For
or
all
1.
I, for all Ci. Okay. Yeah, so first of all, yeah, you are right. So first of all, first constraint set of constraints is the xi's are either 0 or 1. Second constraint is
That for all ci,
for all
for all I,
clause, the Ci define.
xi1 plus xi2 plus xi3
Okay,
is
so let's
greater
go.
than equal to 1.
yi1
Okay, right.
plus yi2 plus yi3 is greater than equal to 1, where yi1 equals to say xj if yi1 is equals to just xj, and no, not y, if
So we'll have to change a bit of the notation because in the
this clause xh, sorry,
so we'll have to change some notation, right? Because in the clause form, that is not a general clause, but we could have the bars.
no, that's
above
what I'm
it,
saying.
right?
I'm writing.
Oh, okay.
Hold on. xi1 equals to, so maybe I should have not used clauses. So the variables are a1 to an. Okay, that might be better. So the variables are a1 to an. Ai clauses are this. This is equals to aj if this is equals to aj, and equals to 1 minus aj if xi1 equals to aj bar. Okay, and that's it. Right? So now question is that what do you have to prove? So you have to prove the two things, right? First of all, so proof of theorem, proof of correctness of the reduction. If phi is satisfiable, oh, I have not yet told this one. What is this ILP thing? Okay, variable cost. And what is it I'm doing? You maximize one. Okay. No, so you minimize, right? So you minimize, so maybe minimize 0. And this k that we are talking about, so that is equal to 0.
So we should technically have minimized 1, right? Because we want the output to be 1 if all the equalities are satisfied. Because they're already giving us 0 if they're not satisfied.
The IPL instance, ILP instance says that this is 1 if there is a satisfaction thing which is less than k. This
So-
one here doesn't matter.
Oh, so then there is no minimization problem then, right?
It's a minimum problem.
Or we're looking at C transpose X has to be lesser than equal to K. So there is no
Yes.
minimization, right?
C transpose is less than K. So I will output 0, and question is that K equals to 0. Is there a way of solving X such that the output of the ILP is less than or equal to K?
Okay.
Okay, so that's how the minimization thing happens,
Can-
right?
Repeat, sir.
So this 0 here, it doesn't matter. Okay, I can put any number over here. Okay, so let's call it one.
So here this K is what?
So ILP is an optimization question, right? It says
Yes, sir.
that under this constraint, under the set of constraint, minimize something. Okay. But when we are talking about NP completeness or NP or any of them, we have to talk about decision problem. So what is the decision problem that we are talking about? The decision problem we are talking about is that, is there an ILP solution? Okay, or is there an output, okay, of this solution, of this instance, which is less than K?
Okay, sir. Okay.
There is no K there. I didn't.
So K is not in the ILP instance here. K is another parameter that isn't given. So this is exactly how you convert any optimization question to a decision question. So in optimization
sir.
question, you optimize something, and decision question is that, okay, is there a solution that is less than this? Okay.
So we are dynamically selecting K in a way to, like, we do bubble sort, or like greedily we are taking K to get the minimum.
Yeah. So if you have to solve the optimization problem using the decision problem, then that's what you have to do. Yeah.
So because any linear combination of X's will definitely be at least 0. That's why we're taking K to be 0.
No, it doesn't matter. You can take K to the P. Any P is fine. I'm saying that even 0 is also fine.
Okay.
Okay. Well, this idea is that what is the output of this answer as this algorithm? Can you tell me? Just this. What is the output of this?
Yes, if the conditions are satisfied, then it is 0.
If the
Otherwise-
conditions are satisfied, then it is output P. If the conditions are not satisfied, it doesn't output anything.
Oh, right.
If the conditions are not satisfied, then what?
It outputs nothing.
Okay.
It's the empty set. You are asking, give me the lowest point of the empty set. Okay. So here, therefore, what you have to prove is this following thing, that if phi is satisfiable, then the ILP has a solution. Okay, or that means the constraints are satisfied. That is one thing that you have to prove. Let me call this one A. And you have to prove the second one, the opposite, is that the opposite, which is basically if phi is not satisfiable, then ILP has no solution. Now, I mean, how will you prove it?
So if it is satisfiable, then
Yeah.
that means there exists some assignment of AIs such
Which is-
that
Yeah.
the such that the formula is evaluating to 1,
Yes,
which
sir.
means that
Yeah, go ahead. Which means that every clause has at least one has at least one of them evaluated to true.
right.
Right?
Yes, sir.
And the formula here means this inequality over here.
It's just mapping the true to 1.
Yes, it's basically this one is evaluating one clause. So if so one thing is that okay, so what is the solution? So whichever in the solution of the CNF, whichever AIs is put to true, you put it to be 1 over here. Okay. And now question is that if a clause is satisfiable, that means at least one of these 3 things has to be 1. And then you can show that means these 3 things adds up to at least 1.
Yes, because all of them are non-negative, and if any one of them is 1, then the sum has to be greater than equal to 1.
Exactly. Okay.
And since this holds for every single clause, then every single clause will have
Right. So every single
will
clause is
satisfy the
satisfied, which is all that we need.
yes,
Right. Now the opposite also we have to write it, right? Which is
right,
that
there exists a clause which will have to be 0.
Or the other way, best option is usually people do the other direction. So in that sense, okay, let's say the ILP has a solution. This particular ILP has a solution.
Okay, right.
Then how can I get a solution for this SAT instance? Whichever AIs are 1, you put them to be true there.
Right.
And that's it.
Okay.
Is this clear? I mean, I'm not giving you I didn't write the whole proof of it, but I'm sure you can finish this one. But did the arguments? I mean, are you guys all fine with the arguments? Or should I repeat it? Repeat some part of it? So these reductions are actually sometimes quite tricky. Okay. So you should realize this one. So they are not at all obvious. Although we are going to deal with some very simple ones, the reductions are quite non-trivial.
So, sir,
Yeah.
finally, we didn't actually found a method to solve the optimization problem. We basically converted it to a constraint problem and found the solution.
I mean, we found a constant problem and with a K to be, yeah, exactly. Yes. But that's good enough for us, right?
Yes.
Okay, so let's kind of maybe, if you guys are comfortable with this one, so I will give you an assignment on this this NP completeness, and in which I would insist you guys to write the proof of them. And see, this particular problem, this particular reduction was a easy reduction, and proof is kind of easier. Usually the proofs are not the hard part. Let's put it this way. The proofs, you can think of it and you will get it. The hardest part is actually the construction of the reduction. So let me give you another problem, and I will ask you guys to think a little bit more. I don't know whether we have time today to solve it actually. Basically, I want you to prove that vertex covered is NP complete. Now, what is vertex covered? This is again the same thing. What is vertex covered? So the input is a graph G, say V, E, and a number K. This is important. Again, the same thing, same K is coming up. And the output, okay, is 1 if there exists a vertex cover of size less than or equal to k and 0 otherwise. And what is the vertex cover? A vertex cover is basically a V prime subset of V such that every edge EI, EJ, sorry, every edge, say VI, VJ in the edge set, at least one of them must be there. So V prime intersection Vi, Vj is not empty. So every edge must contain at least one of its endpoint in the vertex covered set. So can you please, maybe you can ask some people who have not been talking that much. Shoutim, are you there? Shoutim?
Yes, sir.
Yeah, so do you have any idea about how to, or how will you go about it? Let's say, what do I have to do to prove the vertex covered is NP complete? Hello, Shoutim?
Sir, I'm thinking.
Okay. I mean, give something. I mean, what are you thinking? Can you just? Okay. Chandramouli? Chandramouli, are you there? Hello. Jyotishko, are you there?
Yes, sir.
Yeah, can you just tell me? I mean, I don't want a reduction to straight way. Just tell me what is it that we should do?
Sir, are we assuming here that VC is already in NP?
Yeah, you
Or,
can think. Yeah, let's think of VCs in NP. I don't want to go into that. Yeah, good. So that is the first
Okay, so
part.
we need to show that SAT can be reduced to VC.
Ha. So one option, okay, so to prove the first step that can have that you have to do, okay, so the first step, now this is something that I should again repeat here. First step is to prove, so find a suitable NP complete problem L and prove L is easier than vertex cover. So maybe, as you say, maybe, so for example, we can try to prove, say, let us try to show SAT is reducible to NP. So somehow it's like when you solve a problem, right? You try to use the, like you guys have used things like, say, Chebyshev's inequality, right?
Sorry, sir.
In your proofs and all, you have used the Chebyshev inequality in statistics. You use, right?
Yes.
Yes, sir.
But Chebyshev's inequality also follows from Markov.
Right.
But you don't go back to Markov all the time. You use Chebyshev, right?
Yes.
So
Sir.
similarly here, to prove something is NP complete, you don't necessarily have to go back to SAT all the time. If you want, you could have tried to prove ILP is in less than VC. That also is perfectly fine. Okay.
Yes. Sir.
That is also good enough. So which is easier, that I don't know. Both of them is true possibly, but one of them is easier to solve. Okay. And then you start with that.
Sir, I'm having some problem understanding. I mean, how do we formulate these problems at all?
What speed problem?
I mean these problems, like this VC problem, as these the string of numbers like that.
I don't understand. What do you mean formulate the
Oh,
problem?
I mean like those clauses and everything.
I'm really not understanding. What do you mean?
Sir, I mean, how are we formulating this any problem, any NP complete problem or any problem in terms of those clauses and those I mean those C1, C2, all these things.
What do you mean by formulating? I'm exactly not understanding what you mean by that.
I mean representing maybe.
Okay. So, okay.
Can you please fix any problem and you can just
Okay,
consider
let
this
me
word
let,
stuff.
let me forget all of the problems. Okay. Have you done graphs?
Yes, sir.
Okay. How do you represent graphs?
Through an adjacency list or a matrix, adjacency matrix.
You represent the adjacency matrix, right? Or adjacency
Right.
list.
Right.
How to write an adjacency list matrix? Adjacency list. It is just a set of stuff that you say. It's a matrix. Okay. Something
Right.
like that. 1 0 0 0 0 0 0 1 0 1, some kind of stuff like that. But when you view a graph, do you think of it as adjacency matrix or do you think of it as like this? Something like that.
Right, sir. Right.
So there are two representations. One is an intuitive representation, one is a formal representation.
So in case of any general problem, any
Now,
arbitrary
in the
problem,
case of a SAT, say, what is the representation? What is this? You have these variables, right? So you have n variables. Okay. So I can think of it as n variables as, so I can think of the n variables as, say, the n variables are, say, 1 to n. Okay. Or so maybe I can write it as a so let's say x1 to xn. And I have clauses C1 to Cm. Now each clause is what? Each clause is nothing but a subset. This is a set of x, subset of x, such that Ci has size 3, exactly 3. Sorry, no, x union x complement, such that, okay. And that is all that you do. You represent, so the input or an instance is a set x and a set of clauses C1 to Cm. That's it. Now, if you say that, how would you represent C1 to Cm and x? Yes, I can represent in a 0 1 string also. But that's an encoding. Okay. In the case of ILP, how was I representing ILP? What was an instance? It had only 3 points, right? It had a C matrix in R to the power n, a B matrix in R to the power m, A matrix, sorry, C and A are vector. So maybe this is what I should write as, what is n cross 1, m cross 1, A is in R to the power m cross n, and that's it. Once somebody gives me the and a value k, which is in n. This is the input. You have 4 you have for 2 vectors, 1 matrix and one number. What is it says?
AC is less than or equal to B, right? So we want AC less than or equal to B, right?
No. I don't.
Sorry, sir. Yeah.
I want to. So this is C. So question is that the output. Okay, so this is the input. The output is 0 if, sorry, not 0, is 1 if there exists x
Such that ax less than equal to b.
such that ax is less than or equal to b, x is bigger than 0, x is in natural numbers cross n, and c dot x or c transpose dot x is less than k.
Yes, sir. Yes, sir.
See, anything can be represented in 0, 1 string, okay? But if we have to talk in binary language, then you will not understand a shit. Okay, so that's why we are talking in the language which is slightly understandable for us.
Yes, sir. Yes, sir.
Namely graphs, namely IL, namely the inequalities, namely SAT. Okay. So now are you convinced that these problems have a formal definition?
Yes, sir. Yes, sir. Absolutely.
Okay. Now tell me what you have to. Yeah. So how do you go about it now? Of proving this thing? Shoutin Das?
Yes, sir.
Yeah.
Sir,
You have some idea?
so that ILP will be complete.
Sorry. I can't hear you.
Complete.
Can you come closer to your mic or something maybe? Okay, I think we lost something maybe. Okay, so what do we have to prove here in this case? So one thing is that we have to first find out our correct thing. So let's start with this, okay? I will take an instance of SAT and convert it to an instance of the vertex cover. Yes, Chotim says that, yeah, we have proved ILP is in NP complete. That's true. Yes. So you can, if you want, you can reduce from ILP also. Okay. You can take an instance of ILP and try to write and to convert it to a instance of vertex cover.
So in the SAT problem, if you want to reduce it to a vertex cover problem,
right?
We're looking at clauses in which we want at least one of the literals to be satisfied, and that could be something like if we were to make a graph in which every one vertex is either a1 or a1. So let's just take a graph which has a1 through an as vertices, as well as a1 bar to an bar. I mean, this is just a preliminary construction. We might have to adjust this. And if we make, for every single clause that there is, if we make a triangle.
Very good, excellent. I mean, did you guys? I mean, you really came up with this idea by yourself?
Yes, sir. But then there's a problem now, because
that's fine. You can fix that problem, I'm sure. Okay. So
because the vertex cover problem is trying to say at least one of the vertices has to be included, and if it is included,
right,
then this whole clause gets satisfied in the
so good.
This whole triangle.
So let me just try to explain to. So what is it that we want? We have been given now a phi, which is a CNF formula, right? Which is basically phi is actually nothing but C1 and C2 till and Cn. And Ci is equals to, as we pointed out, is xi1 or xi2 or xi3, right? Now I want to note again, I'm repeating it, this is something very important. I want to reduce SAT to vertex cover, not the opposite. To reduce SAT to vertex cover. SAT is known to be NP complete. We want to prove this is NP complete. So we are reducing an NP complete problem to this. Okay, so the way to go about it is you start with a SAT instance. Okay, and then I want to kind of, given a graph, I want to given a formula, I want to create a graph and a value k such that phi is satisfiable if and only if the vertex cover of g comma k equals to 1, meaning g has a vertex cover of size less than or equal to k. Okay, now this requires some real ingenuity, although it's kind of, I mean, during the 80s and even 90s and even later on, actually coming up with ideas like this was considered to be really the main one of the main focus of the CS community, that how to prove various problems is NP complete. So I don't want to really tease you guys, but instead I will try to give you the reduction. Okay, now what is the reduction? So here is it. Okay, so I have this, so I have the variables which is x1 to xn, and I have this clauses, right? So to define this graph G, what will be my vertices? So my vertices are, say, A1 to A, or maybe I should write not write A1. Okay, so U1 to UN and V1 to VN. Okay, and I have another set which is WI1, WI2, WI3 for I going from 1 to M. So that means I have, and the main idea is whenever you reduce this thing, you should think of what is it talking about. This one, U1 and V1 is basically kind of talking about the variable x1. The idea is that this is x1, this is negation of x1, basically. Okay, so I can write it here. U1, V1, U2, V2, U3, V3, U4, V4, and so on. Okay, so in some sense, the UIs are the variables and VIs are the negation of the variables. Okay, now what are these WIs? So WIs corresponds to the three variables corresponds to the three clauses for each clause. So I can have a clause for here, I have a clause here, I have a clause here, something like that, right? So there's three clauses.
So are we treating Wijs as vertices on their own, or just
on their own? On their own. Okay.
Okay.
So this is a set of my vertices. So how many vertices are there? 2n plus 3m. Right. Now let me draw the edges. What are the edges? First of all, yeah.
What are the triangles that you've made? Those triangles are a single vertex, right? One of the triangle is one single vertex.
No, so like this one, sorry. So this is W11, W12, W13.
Oh, so even though W11 would be equal to one of those vertices in the upper.
Yes, it's a different vertex. Yeah. So
It's a
every
copy
clause
of
have
it.
a different vertex.
Okay.
What does M represent there?
M is the number of clauses. Oh, sorry.
Okay.
M is the number of clauses that was there. Okay. Now, what is the main idea? That see, I first of all want to choose a set of vertex cover. Okay, I want to force this graph to have a vertex cover. Okay. In such a way that this vertex cover should basically be helping me to find out the solution of the formula, right?
Yes, sir.
And the opposite, the formula will help me to find out the vertex cover. So in this setting, I should not be picking two elements. I should be picking exactly one, right? Because this is basically corresponds to x1 and x1 bar. This corresponds to x2 and x2 bar. Now both cannot be positive, right? But
Yes, sir.
exactly one of them has to be positive. So a vertex cover must take one from these two, one vertex from these two. In fact, exactly one from these two, and so on. So first of all, I can say that, okay, let me just add these edges. So what this helps us is that this says that, okay, it has to have at least one from, so at least one of each variable has to be true. Means either x1 or x1 bar, or xi or xi bar. But that doesn't guarantee that both of them cannot be one. Okay, maybe both of them are one, maybe both of them are in the vertex set. So that's not good. This is the first part. But then, what do I do? Okay. Now, the certain thing that I'm going to say now, I myself don't have a very good explanation of why this construction was done. I know how to give the proof, but the intuition of the constructions are sometimes a bit shrouded in mystery. It's kind of a bit of a, you tried it out and solved it. So another idea is that, okay, you put triangles here. Okay. Now, once you have triangle, so you have to have among this, like these things, how many vertices has to be picked up out of these three?
Two of them.
Two of them, because if you take just one of them from these three, then if you take this one, then this one is not covered. So at least two of them has to be picked up from each of these variables clauses. Okay. So at least one has to be picked up from each of them, and at least two of them has to be picked up from each of them. Okay. Now, yeah. Now here
No,
is
sir,
this.
not,
Yeah, go ahead.
no, sir, nothing. Sorry.
Now the next thing that you do is that, okay, now we have talked about these variables. Okay. Now these variables are there, the clauses are there. We have to somehow connect these variables and clauses. How will you connect it? A natural way is to connect them as it appears. So in this clause, maybe you have x1, maybe this clause, I can write this clause, say, so this clause is, say, x1 or x2 bar or x4. In that case, what I do is that I will connect. See, this is a variable for the x1, right? X1 meaning the first vertex variable of the clause is demarcated at W1.
Sir, could you please repeat this part?
Okay, so the clause says, look at this clause. Okay, this clause. So this clause says x1 or x2 bar or x4. Okay. Now I will draw edges between this set of vertices and this set of clauses in a clever way. What will I do? First of all, this clause, there are three vertices, right? This is the first vertex, the second vertex, the third vertex, right? So the first vertex corresponds to the first element of the clause. Second vertex is this. Third vertex is. So in some sense, this first vertex, what this says is that this vertex is x1. but x1 is here. So what I do, I will connect x1 with this first. Okay. Then the next, this is the second one. Second one is x2 bar. X2 is this. So this is x2, this is x2 bar. So what I will do? I will connect this. The third one is what? It's x4. X4 is this. So it is x4. So I will connect this. Now I continue like that. Okay, so this is my graph. Is this clear? The graph construction at least?
Yes, sir.
Yes.
Okay.
So,
Now,
so
why-
we're not connecting the vertices which have the same literal across two different clauses, right? We're connecting it to the upper set, but we're not connecting amongst.
No, we are not
These.
connecting between this and this. No. We're not
No, sir,
connecting-
even in the bottom row.
We are not even connecting this and this.
Okay, so these are independent sets.
Yeah, in some sense. But if this is say, if this one is say x1 or x2 bar or x3,
Right.
okay, or say x1 bar, x2 bar, and x3, then see this corresponds to x1 bar. So I will connect it from here. This corresponds to x2 bar. So I connect from here. This corresponds to x3. So I connect from here. Okay.
Yes, sir.
Now, why is it? What is the useful thing of this? First of all, okay. So let us say that there is a satisfying assignment of the formula. What does it mean? That means there is a set of solutions, right? It's a set of assignments of the formula such that every clause is satisfied. Okay, fine. In that case, what do I do? Consider all those vertices which are satisfied. Okay, say, sorry, also say it says that okay, here satisfy this one. So this is the satisfying assignment of the CNF or of the SAT. Okay, here you satisfy this, here you satisfy this, and here you satisfy this. Something like that. Okay. Now, what happens here? What are the vertex cover for me? See, this particular one has covered this. This has covered this, right? Note that for every clause here, since I know that the things that I colored green ensures that every clause has at least one satisfying literal. So that means for every clause here, there exists at least one point here that is connected to it, which is colored green.
Yes, sir.
Correct. For every clause, there exists at least one vertex which is connected to a green vertex. Okay. So in that case, what I do is that say for in this clause here, this is connected to here. So I will say that okay, then I will color the other two. So in this case, I have two vertices that are connected, this and this. Okay, I will color this one and so on. And these are my vertex cover. Okay. Okay, no, this will not do. I have to color at least one here. So I'll just color two things. I'll color one here and at least not one here. I'll color two. So every clause, therefore, now what happens? Let's see. Is this a vertex cover? First of all, note that all these horizontal vertices, edges are covered because every clause, every variable, at least one of them has been put to be true, right? That's by definition. In every clause, the triangle, two of them are picked. So these triangles are picked up, done. Okay, all the triangle elements are done. And what about these colors that are going here?
So they have to be covered because in the first step, at least for every single triangle, at least one of them was already saturated by the first assignment on the top assignment.
Right. So take any edge over here, right?
Right.
Take any edge over there. Then the two things can happen. Either this edge connected to a vertex here.
Right.
Okay. And in that case, maybe this vertex was not picked up, but this is already covered by here.
Yes.
Or if this is not there, right? Then there is some other vertex was picked up here. So maybe here, right? Or this is not the one. Say this one. Or oh god, not a very good job. Say this
So,
one,
but
right?
if you're considering a specific edge, we're
So
going to be looking at its endpoint, right?
yes, so look at this edge. We are looking at its endpoints. Okay.
Right.
Now here, if V4 is not picked up, okay, so this technically can it be not covered? But because this is connected to a vertex here, which is not colored green, so there must be some other vertex here that is colored green, right? So which is in this case here. So in that case, in these three things, these two must have been picked up, or this one must have been picked up. Did I confuse you guys?
So is the argument saying that we consider any cross edge in this sense, which is crossing over from the top row to the bottom row, and we're looking at what happens?
Yes, so we have
Is
to
it
prove
saturated?
that either we have to prove it that either the top one or bottom one is picked up. Right.
Right. So in order to prove that, are we saying that we have to see whether it is saturated or not after the first assignment, the initial assignment on the top rows, which was
Yes.
the solution, the proposed solution that we had assigned.
Yes, yes. If it is done, then we have. If the top one is still picked up, then we have nothing to be talking about, right?
Right. And if it is not saturated in that,
I claim that the
means,
bottom one will be picked.
and that is because that in that triangle,
Yes.
some other vertex was
was kind of so like this vertex was not picked up because this is what. So how did we not pick up some vertex? Right.
Because they were already considered.
Every clause, one of them was there, right?
Right.
Because of the connect. So that is the vertex that is already. This is connected to this vertex that is already covered. I pick up the other.
Right. Okay. Right.
How are we starting?
How are we starting what?
I mean, so we are not picking up the other vertex when we have picked up one.
Okay, so I mean, when we have picked up one. So first of all, okay, so let's see. Okay, so maybe this is something. So I have a satisfying solutions, right? Okay, so what is the vertex cover? So say let x I1, xi2. It's not a good idea. Okay, so maybe I should define it. Okay, so what is the satisfying solution? So I have a set of variables x1 to xn, and they are either have been mapped to true and false. So this is a function, right? And this is a satisfying assignment to the formula phi. Okay. Now, if this is the case, then this is what I will do. Okay. In my vertex cover, okay, now that I have these variables u1 to ui, right? Okay, first of all, I will pick, okay, so I will pick up ui if v of xi equals to true and vi otherwise. Okay, so in these two things here, either if this is if this is true, meaning if that this is equivalent to x1 is false, okay, then I pick vi, and otherwise I will pick the ui. Fine. Now I will have to pick some more other vertex. Okay. Now for each clause, for clause ci, okay, or cj maybe, okay, we know that f satisfies cj. What does it mean? That means that, so if, so what is cj? Cj is equals to say xj1 or xj2 or xj3, right? At least one of them is true, right? Right? At least one of them is true. Right? So say if I say that, okay, so let f of xj2 be true. Okay, so I mean without less of generative, we can say that okay, this is true. Okay, so that means this variable here means this function, or maybe this is not the one. So this one is getting satisfied. This particular variable or vertex is the good vertex. Done. Okay. In that case, you put the other two, which is xj1 and xj3, in vertex cover. Okay. Is this clear now?
Yes, sir. So by the construction, that means for every triangle, it will have a structure where two of the vertices are selected.
Right.
And then the third one that is not selected, we retrace it to the top row.
And that is already
one is
in
selected.
this vertex.
So by this property, we can already establish that every single cross edge will have to be saturated.
Exactly. Okay, so this is, so now I have one thing that I have not told you is that, so I have started with this CNF formula and I converted this graph, and I kind of told you that if it is if the formula is satisfiable, then this is it has a vertex cover. But vertex cover of size how much? Can you say what is the vertex cover of size how much?
So it will have to be 3n.
No, it's not 3n.
N plus 2 times m.
Yes. Okay. Now I let you guys go back and prove the other direction, that if this graph, okay,
has a vertex cover of
size less than this, then that must be satisfied. And why is it that case? The main trick is that to cover this vertex, right? Cover this vertex, at least one has to be there from each of them.
Yes.
And to cover this set of vertices, at least two has to be there from each of them.
Right.
So that means because it is just, so n plus 2m, so in fact exactly one has to be there from, so if it has a vertex cover of size less than n plus 2m, exactly one has to be there in each of the top ones, and at least exactly two has to be there in each of the bottom ones.
Right.
Okay.
Yes.
So I'll let you guys to go back and think a little bit on this particular problem. Okay. It's not hard. Once somebody tells you that this is the construction, it is not hard. Just by seeing it twice, you will understand it, what's going on. Okay. But remember that this is something was done by someone, and this is something that you will have to do it yourself also. Which means the trick behind it is about these reductions. How do you come up with these reductions? What goes on behind this reduction?
So any vertex cover of n plus 2m vertices, since it will have this structure, we just have to show that there can't be any, since every single cross edge is also satisfied.
Yes.
That means that there can't be any triangle which has two selected vertices and no selected vertices in vertex in the
Correct.
top row.
Exactly.
And hence that means that has to be a vertex cover of
Yeah.
this triangle setup. Okay. Right.
So what about the rest of you guys? Are you guys, how many of you are sleeping and how many of you are awake?
Yes, sir. This is fine. Sir.
This is fine.
Sir, the problem is that these kind of things are somewhat, complicated. Seems complicated actually.
I mean, the
So-
construction is a bit complicated.
Yes, sir. Yes, sir.
Coming up with the solution is quite complicated.
Yes, coming up with a solution is quite complicated. There's no doubt about that. Okay, so pick up any book. There will be lots and lots of examples. We will do some more actually in the next class. Okay, and I will be posting a collection of other collection of these kind of problems, and you have to do a little bit of practice. If you do a practice, it will not be hard. Okay, but the main idea is that once you have to start thinking in the right direction, meaning you have to start thinking, I mean, yeah, I mean, like it's just something that you do by practice.
Sir, can you please share today's recording with us? Because it's better if we go through it once again.
I mean, every recording is shared.
Yes, sir. Yes, sir. Yeah.
Yes. Yeah. So yeah, please go over it. Go over it slowly. Okay. Try to formalize it yourself. Again, as I told you, formalizing it is not the hard part here. You guys will be able to formalize it without any problem at all. You should think about how did they come up with this construction. So we call them as gadget constructions. So this kind of so this kind of stuffs are called gadgets. Like every clause is put a triangle. This is a kind of a gadget for array or these things. Okay. So this is something that we have to do it slowly. Okay. So okay, so I think I will I'll post a set of problem set on this problem, on this set of reductions and all. Okay, and you guys go over it as much as you can. We'll come back next class and do some more of these reductions. And this is kind of very important, this reductions concept. The fact that you can do reductions from one to the other and so on.
Sir, shall we have an offline class in this week?
I will try to have a offline meeting at least in this week. So yeah. So today there was nobody. So who usually go to this? Chandramouli, you go there? Or?
Sir, I go to the class.
You go to the class, right, Jyotish? So today
Yes,
today you did not go, right?
Yes, I went to the class, but I mean, since it was, I attended the first class in offline mode. Right now I'm not in the class, so I'm
Okay.
attending the class from my own mobile phone.
Okay. Okay. I will let you know. Okay. So let me
Okay,
have
sir. Okay, sir.
Sure.
Thank you, sir. And is there any update about our mid-sem performances?
It will be. I will be done. So I'm almost done. I have a couple of papers that are left to be corrected. I'll be done by next class.
Okay, sir. Okay, sir. Thank you. Thank you.
Okay. Okay. So thanks.
Thank you, sir.
Thank you, sir.